All right, well, welcome to week 3, moving forward. So we seem to be in a brave new world of internet today, where there's no more captive portal, and you're like always connected. It looks glorious, man. This is like living in the 80s all over again, because I can just like turn my laptop on and connect to the server and get web pages and stuff like that. It's pretty awesome. I don't know if this is permanent or if it's transitional or what, but embrace it for now, because this is the good life. Yeah, yeah. This is good, so I can like.
Is that your screen?
Look at that. Just connected to the server. That's my background. I don't know what it is.
You would never expect to see that.
Yeah? All right, so a number of things I want to go through today. I want to talk about ODP 208. I want to discuss PA1, which looked really good. I was really happy with what people did on PA1. I want to go through some sample code. I want to refresh on putting things into separate files, using include files, using .h files. There's still a fair amount of confusion around that, and it's still optional, but if you want to do that, I want to make sure we've gone over that once more, and that'll lead us into Makefiles. I want to look at PA2 type structures in GDB a little differently from last week. Talk about different variations on linked lists, what happens if we get rid of the Sentinel. I want to talk about circular lists, I want to talk about doubly linked lists, and then we're going to leave lists and we're going to start talking about hashes, hash tables, hash functions, and hashing for the next few days. So that's our general agenda. Any questions up front before we jump into all of that? I also posted an announcement on Canvas. Tomorrow and Friday I will be available at 8 o'clock. But I won't be in my office, I'll be in the digital lounge. So if you got feedback from me on your assignment saying let's talk this week, please come and see me this week. If you can make it to the regular 9 o'clock hours, I'll be in my office at 9. If you have class at 9, you can find me at 8, digital lounge, and we can go through algorithms, we can go through your code, we can whiteboard it, whatever's going to help. So that's this week only.
Thank you. Oh.
Sorry?
10?
Anything for 10? What do you mean?
Around 10,
I have class at 10. Tomorrow I have class from 10 till 2. You have class at 8? All right, so 208, you are building a small linked list. You're making a function called build. It takes 3 integers and it builds a little linked list containing a Sentinel node, 3 data nodes containing those integer values. And it's a linked list because Sentinel points to the first node, that points to the second, points to the third, and the third points to null. And you return the address of that Sentinel node. So if you wanted to test this from a main program, you could say struct node list equals build 10, 20, 30. And when it comes back from build, list should be the address of a Sentinel node. So if you printed list arrow next arrow data, it should print out a 10. And if you did list arrow next arrow data, it should print out a 20, and so on. Or use temporary variables to avoid the arrows. So how do you do this? Your build function, it needs to have 4 struct node stars. It needs to call malloc 4 times because you have to build 4 nodes. So call malloc 4 times, save those return values. You can call it Sentinel first, second, third, or whatever you like. And then Sentinel arrow data, we don't care what the value is. Sentinel arrow next should point to first. And how do we do that? This can be confusing. So let's just say you have two nodes, a Sentinel and a first. Call malloc. How big do we need to allocate space for? The size of a struct node. Good. Without the star. And then first is the same thing. So here's the Sentinel. Here's first. Each of these is a struct node, has a data piece, has a next piece. If we want to create this link, here's all you got to do. Right, just Sentinel arrow next equals first. So Sentinel arrow next, that's this block of memory. The thing that Sentinel points to is this structure. The next field, that's this block. And first is a pointer. It's the address of this node. So this assignment statement takes the address of this node and puts it into this location of memory. That's what's implied with all these arrows that I keep writing. When I put an arrow saying this points over here, it means the address of this node is stored in this location. And that one assignment statement sets that up. If I want to set first as data, I could say first arrow data equals X in this case. And that'll load X into this field. And I can have first arrow next point to the second, and so on and so forth. And what do we return from this? We want to return the address of the Sentinel. How do we do that? I'll start it for you.
You can just return Sentinel.
Just return Sentinel. And when that makes sense, it seems really obvious, but it's not obvious until it makes sense. Because you might want to do ampersand Sentinel or something like that. So the thing to keep in mind is Sentinel is a pointer. Right? It's the address of a node. It's the address of this node. And we're asked to have build return a pointer to a struct node. And we want to return the pointer to the Sentinel, so what we should return is the address of the Sentinel, and that's what SENT is. So if we return SENT, that's returning the address. And that's probably to me, that was always the most confusing part of dealing with these structures in memory, was when you use an ampersand, when you use a star, when you just use the bare variable. Why is it this instead of address first, or star this, or things like that? And keep going back to the memory. Right? If you've done 270, this may help, but keep going back to what these things are in memory. Make yourself a little memory map. Right? Simplified memory from, say, 0 to 10, kind of like an array, hint, hint. And pretend that malloc gives you, this address for sent, so set sent equal to 2, for example. But remember that that's an address in memory. And first maybe is equal to 5, that's an address in memory. And now go to location 2 and pull off the next field and set that equal to 5. All right, so pretend you're a computer, work on a simplified memory model, and try to make peace with these kinds of things. Okay, once you can do that, you can do ODP 208. Once you can do ODP 208, you can do PA2. Everything you need to know in order to do PA2, you will know once you've done this. You probably already know it, actually. But you'll know it for sure once you've done this. Because you're mallocing, you're manipulating pointers, you're grabbing fields of things pointed to by pointers. That's really all there is. That's the only difference from PA1. So time spent on this is well worthwhile. You can write your own main program. You can go into GDB and mess with it that way. I'm a fan of just pencil and paper. Do a memory map. Write some code. All right, questions on the ODP? All right, so let me talk about PA1. So PA1 looked great. Pretty much everybody seems to understand linked lists, the basic concepts, and seems to understand the algorithms for manipulating linked lists. Most of the issues that got into pretty major point losses, other than things that are easy to fix, like you didn't put spaces between your numbers when you printed, or you didn't put your name anywhere in the program or things like that. Other than the easy issues, the two main types of point deductions were, one, implementation details. So the comments say, okay, we want to move through the list until we get to a number that's bigger than num. But your while loop might start with the wrong values for previous and current, right? So just details in how you take the algorithm and convert it into C. That was one set of things. The other thing, and this was probably the most common large deduction, problems with the main program. Problems with fgets, scanf, looking at return values from scanf, things like that. And that can cost a lot of points, because without the main program working, I can't really exercise the other functions. I can only look at the code. But those are basically like CSE 224 concepts. And if you got tied up in those issues, right, definitely come and talk to me and let's nail it down, because every case you had the right pieces, right? It's just you got to check the return value from scanf. You've got to scan for the right kind of pattern. You've got to make sure that if you're scanning, if you're doing an fgets into something up to 100 characters, you got to make sure that something has space for 100 characters, right? It can't be a single character. It can't be an array of 2 or 3 characters, stuff like that. So it's stuff that I think is pretty easy to hammer out. But until you hammer it out, it interferes with developing your other modules, testing them, coming up with the main program, and so on and so forth. So definitely let's get together and talk about that. So implementation details, most problems manifested themselves in the delete function, or the add function. So search was fine, print was fine, get node and it node, release node seemed to be fine, and it seemed to be fine. Add function, biggest problem was getting the thing started in the right way. For example, you have a Sentinel node at index 0. So I see code where we would say previous equals 0, and then current is supposed to be the node after previous. If you set current equal to 1, that might work in some cases, but it might not in others, because you don't know that the node after the Sentinel is at index 1. It could be somewhere else, right? The first time you insert it is going to be at index 1, because that's the first free node. But if you add another node and then you delete that first node, or you insert something before it, the node after the Sentinel could be anywhere in the array. And then delete, sometimes delete would go crazy and like wipe out huge swaths of the list. And all of those things are usually just you're trying to update a pointer to here and you accidentally put it to there. And it can be as simple as you meant to use temp1 but you use temp2 or something like that. And how do you find those? Well, you find them by walking away, right, after you think your program's working, take a break, clear your head, come back, and then just debug the heck out of it. Just throw all kinds of test cases at it until you get it to fail. When you get it to fail, try to narrow that down to a small test case, so you only have to do 3 things before it misbehaves, and then go inside GDB. set up breakpoints. If the delete's misbehaving, put a breakpoint at delete. Do your 3 things. Do the delete that's supposed to make it misbehave, and now you got to go through line by line. And you got to be looking at your code. You got to be keeping track of the variables. You got to keep the algorithm in mind and see where the code and the algorithm diverge. And there's really no other approach. But you know, if your delete function is 15 lines, you only got 15 lines of code, and there's probably a while loop with 5 lines inside. So you really just got to go through those 5 lines until you get to a disconnect. All right, so come and talk to me, and we can go through your code. We can put stuff on a whiteboard and do this together, and get some practice at that and figure out what's going on. And you want PA1 to be pretty rock solid for PA2, right? So even if you spend the next few days finishing PA1, in some sense you're spending that time on PA2, because PA1 will pop over into PA2. All right, so sample code. This was my version of PA1. Which I broke. Close your eyes. Okay, you can open it. I broke this last period. All right, so here's my version of PA1. So usual include, define my null, define what a struct node is, put in prototypes for functions. I did this in one file, main.c. Okay, no include files of my own, no separate files for different functions, it's just one big monolithic. That's a perfectly acceptable way to do PA1, PA2. But as we go forward, we're going to want to start breaking things into different files, practicing with makefiles, things like that. Those are skills you want to develop. So I did this in a single file. We'll see how to modularize it after this. So one definition of my null, definition of a struct node. We've seen this many times. Function prototypes. So the 5 functions that we need from the assignment, plus I decided to do all of my parsing in a separate function called process. I have a function called usage, which prints out what the user is allowed to do, so what the commands are, so that's the help function. And then 2 internal routines, the get node and release node, also in the assignment. So that's all the functions that are being used anywhere. So the main program, this is the linked list. Okay, it's an array of 100 struct nodes. Didn't need to use malloc. Okay, some people tried to use malloc and allocate things dynamically. In most cases, it got them into trouble. I told you could use 100 elements in the array, so you can define it just as an array of 100 struct nodes. Makes life a little easier. Temporary array for doing input. Call the initialize routine. This makes an empty list. So when I say init list, list, which is this array, has a sentinel at index 0, points to null. It's a list with no data nodes. Print out a prompt, and then the main loop is nice and short. Use fgets to read input from the user, and then I pass that to this function process, which does everything that it's supposed to do. Checks to see if it's an I number, and if it is, it calls add. If it's S number, it calls search, and so on and so forth. And process returns a flag saying, should we exit? So if the user says X, process will return a 0, and we just exit at that point. Otherwise, print out a prompt, go back to the top of the loop. And the null not equal to fgets just means if they hit end of file, if they hit Control D, we'll kick out of the loop, and then we'll return at the bottom here. So main program took nothing to write, right? I just deferred to a bunch of other functions. All right, so process does all the heavy lifting for parsing, and this is stuff we've already talked about. So buffer is a string, that's the thing you're trying to parse. List is the linked list. So I switch on the first character. If it's an I, they said I something, and do an scanf. I did something fancy here just to play with this, but you can just do an scanf I%D into address num. If it returns a 1, they said I space number. And if that's the case, go ahead and search to see if that number is already in the list. If it is, if search returns 1, print a message saying it's already in the list and break out of the switch. Otherwise, the number is not in the list, so call the add function. And if it returns 1, say success. If it returns 0, it means it ran out of memory, so print an error message. So this is the end of adding this thing to the list. So otherwise, scanf did not return a 1, so they said I, and they didn't say an integer, so print out a help message and break out of the routine. This thing up here, I was just trying to have fun. So if they just say I and a number, that should be followed by a new line. If they say I and a number and then anything else, this %C will match whatever they typed in after the number, and scanf will return 2. And that'll tell me that there was some kind of usage error. So if you wanted to prevent them from saying insert 10.5 or insert 10 haha or things like that, this would do it. But I'm not requiring that. All right, if the first character is a P, I just call the print function and break. If the first character is an S, see if it's S and a number. If it is, call the search function. If search returns 1, say found, otherwise say not found. And if it wasn't S followed by a number, print out a usage message. That's the ternary operator, so if this is true, then this expression evaluates to found, otherwise it evaluates to not found. And I'm printing %S, so it'll print out either found or not found. It's just a one-line version of an if statement. If search equals.
Interesting.
Yeah, it's a nice use of a ternary operator in a print. Kernighan and Ritchie, when they talk about ternary operator, they use it for suppressing or printing the S. When you print out, 2 tries left, 1 try left. You can capture that using this kind of setup. All right, same thing for D, right? Delete. If it's a D, say D number. If it matches that, see if the number's in the list. If not, say the node's not found. Otherwise, call delete. Assume it's going to be successful because there's no way delete should fail. And if they didn't say D followed by a number, print out a usage. If it's an X, we just return 0, which says we want to exit from the program. If it's anything other than IP, SD, or X, print out a help message. And when we break out of the switch, just do a return 1, which tells the main program, try again, get another command. So that's all the parsing, right? And I wanted that totally in its own function, because that's a little can of worms, right? That has lots of pieces that can break and lots of moving parts, and it's nice to sort of have that separated off by itself. And it just calls a bunch of things, search, add, delete, etc. All right, so the help message is just a glorified print statement, so that I don't have to repeat this everywhere that they typed in something I didn't understand. And then the actual linked list code. So init, this is straight out of an ODP. Right, set element 0, it's a Sentinel to point to null, mark its valid flag, put something noticeable in the data field, clear the valid flag in the other nodes. The add function, we've talked about this before, right? Previous starts at 0, that's the Sentinel. Current starts at where the Sentinel points, could be null. Create a node. Make sure that it didn't run out of space, set the data field, and then we just loop looking for the proper insert point. So this loop here basically loops until the current node is null, meaning the previous node was the last node of the list. And if the current node's data is bigger than what we're inserting, insert before the current, after the previous. So these were just the 2 magic lines we talked about a lot. have the previous point to the new node, have the new node point to what used to be after the previous, which is current. So sandwich a new node in between previous and current, and then return 1 saying we inserted. Otherwise, the usual shuffle down the list, set previous to current, current to the thing after current. If you kick out of this while loop, so this is the end of the while loop, it means that current is now equal to null, which means previous was the last node of the list and you want to insert after previous. So special case, have the previous point to the new node and then have new point to null. That puts it on the end of the list. Return success. Alright, print is just a straight traversal, so start with the first data node. Right, so I talk about 2 kinds of nodes, Sentinel nodes and data nodes. Right, the Sentinel is the first thing in the list technically, but it's not considered part of the list. The data value is not meaningful to us. By data node, I mean the nodes that are actually in the list that we're trying to build. So the first data node is the thing after the Sentinel. So if you actually have 10 things starting with the Sentinel, you got 1 Sentinel, you got 9 data nodes. That's just terminology I'm using in here. So start off with the first data node, and assuming it exists, print out its value, its data value, move to the next node, and just keep looping. And then print a new line at the end. And then search is the same traverse, but instead of printing at each node, we compare the data value to our number that we're looking for. And if it matches, we can return a 1 right there and say we found the value. If we get all the way through to the end of the list and we didn't return, the value is not in our list, return a 0. And some people embellish this by using the observation that if you're looking for the number 10 and you're moving through your list and you get to the number 15, you can stop right there. As soon as you get to a number bigger than what you're looking for, you know your number's not in the list because the list is sorted. So you could return right away there. So that's a nice efficiency enhancement. I took the lazier way and just searched the whole list. And then delete is the same thing again. Traverse the list looking for the number that you pass it, but keep track of the previous also. And when you get to the point where your current node's data matches what you want to delete, then have the previous step over the current. And if your current happens to be the last node, current next will be my null. That'll set the previous to point to my null. So there's no edge case here. And if you're deleting the first thing, then the previous will be the Sentinel, and so Sentinel will point to whatever the second node is, the second data node. So this works fine. Call release to free the memory in the array and return success. Otherwise, shuffle down the list. And if you get to the end of your while loop, you didn't find the node, so return a 0. And then 2 internal functions. So getNode looks for a spot in the array to use for a new node, and this was an ODP also. So just search each node from 1 on in the array. If the valid flag is 0, set the flag, return the address of that node. If you get to the end of the array and all the valid flags were set, then you're out of memory, return an error. And then release node does the opposite of get node. And this number that you're passing is the index of the node you're trying to free. It's not the data value of the node. Okay, your delete function takes a data value. When you say delete 17, it's looking for a node whose data value is 17. So you do the search, you go through the list, you compare to 17, and so on. When you find a spot where your data value is 17, let's say that's index 5, so you set the previous node to skip over this node, that removes it from the list. Now you want to mark index 5 as being available. That's what release node does. So you pass it a 5 and it just sets the valid flag to 0 in element 5. So it's undoing what was done by getNode. GetNode sets the valid flag to 1. That means this chunk of the array is in use. Release node sets it back to 0, says this piece of the array is free. And in PA2, get node is malloc, release node is free. All right, so that's an implementation of these functions. Oh, something else I want to mention, because this has come up a few times. Inside your code, if you have a void function, and you want to get out of your function at some point, you're allowed to return from a void function. Right? People have asked me this, and I didn't understand what the confusion was until this morning. You're allowed to do this. Just return with a semicolon. You're not allowed to return a value because there is no return value. So you can't say return parentheses 0. You'll get a compile error. But if you want to exit your function at some point, you can just say return semicolon, and it'll go back to the caller at that point. And you can do that anywhere that you want, multiple times, doesn't matter. If you don't have a return and you just kind of fall off the end, there's a return implied. But this is absolutely legal to put in as many places anywhere you want in a void function. Just don't try to return an actual value. All right, so I'm going to make a directory called Modularized, and I'm going to copy main.c into that directory. I'm going to cd into that directory. So I've got a new workspace here, and the only thing I have in here is my main program, main.c. I'm going to break this up into pieces, put some stuff in a .h file, throw in some includes, make a Makefile. Okay, just to kind of go through that and see if we can make sense out of what all those parts and pieces mean. But before I do that, I'm making a totally separate directory. I'm going to work in that directory. I have a copy of my main program, so I can do whatever I want here. And if I do something, you know, like accidentally remove my main program, it's not a big deal, because I can go back to my original PA1, and I've still got everything in there. And I can copy main.c into my modularized file, modularized directory. All right, so I'm just making like a workspace. Okay, so I'm going to break this into the following pieces. I'm going to take my process function and throw that into its own file. So I'm going to Control G, tells me I'm at line 47. I'm going to go down to the end of this routine. And I'm going to say :47, dot, write, process.c. So now I've copied that chunk of code into a new file. And now I'm going to delete it from main.c. And I'm going to go ahead and throw usage into its own file. So this is starting at line 47. Put that into usage.c. Delete that. And then here's the routines for actually doing the linked list stuff. So that starts at 47 and goes down to here. And I'll call that ll.c.
And you're using a G to write this out?
I'm using :w, start line, end line, w, file name. Writes everything between those lines into that file. It's a little VI shortcut. So all I have left in main.c is my main program. So I'll quit out of that, and now if I look, I've got 4 files in here: ll, main, process, and usage. And I can just compile by saying gcc-o main star.c. And how many errors do you think I'm going to get?
A lot.
Let's put that into word count. 222 lines of error messages. All right, so there's a problem here, right? Here's the problem. In main.c, I have standard io.h, my null, what a struct node is, my function prototypes. in ll.c, I don't have any of that stuff. I start off and I say void init takes an argument which is a struct node pointer. I haven't told it what a struct node is. Because when I compile ll.c, this is all that the system has. I didn't tell it to look at main.c, even though I said gcc-o main, I listed a bunch of .c files. It compiles these files one at a time. And when it's compiling ll.c, this is all that it sees. So first thing it says is, okay, I need a pointer to a struct node. What's a struct node? I don't know. I should set list 0 next equal to my null. What's my null? I don't know. Right? Error message, error message. So what I should do is put this in the beginning of this file. And this define my null -1, I should also put in the beginning of this file. And since I'm going to do things like call add and so on and so forth, I should probably put these function prototypes in the beginning of the file. And in fact, a lot of my files need to know what a struct node is, need to know what my null is, need to know what the function prototypes are. Now LL has 7 functions inside it, but I could split that into 7 different files, and each of those files would need to know what a struct node is, what my null is, and so on. Okay, I got 2 choices if I'm going to continue down this path. One, take all of this stuff, copy it and paste it into the beginning of each file, each of my .c files. Nothing wrong with that, but it's a lot of work. It makes my files look really long. I have to go through all this before I actually get to code I care about. And if I decide I'm going to change what my struct node is, I got to edit all my .c files that I put this in and change it everywhere. And if I change it wrong in one place, I'll get a silent error that'll blow up somewhere down the road. So how can I take all of this and put it in the top of each of my .c files without copying and pasting?
Make an include file.
Make an include file. This is exactly what an include file is. It's a way to take a bunch of code and include it in the beginning of a .c program. So I'm going to take all of this, so starting from line 7 and going down to here, and I'm going to put it in a file called mystuff.h. And I'm going to delete it from here. Well, I need to know what this stuff is inside main, so instead of typing it in, I'm just going to say include mystuff.h. Well, I still got 222 lines of errors. Right? Because the problem wasn't main, the problem was all these other functions. Okay, so I'm going to say vi star.c, and in the beginning of this I'm just going to say include mystuff.h. I'm going to write that out.
You don't need to include mystuff.h when you compile.
No, because when you compile, now if I say compile ll.c, it's going to look at this file. First thing it's going to say is, oh, I've got to open mystuff.h, see everything that's in there, take that as part of the program.
Just make sure to include it in the tar file.
Make sure you include it in the tar file, right? Otherwise I can't compile. All right, so I'm going to say :n to go to the next file because it said vi star.c. So I'll go to the next file. Well, this one I already included my stuff. I'll say :n to go to the next file. That's my processor, which also calls add and delete and so on, so I want to include there. The last thing I did was I said Shift-O, typed in number sign include, did an escape. If I hit a period, it will repeat that last command. So I just hit a period, it puts it in here. So I'll write that out. :n to go to the next file, hit a period, :w, :n, and that's the last file. So now all of my .c files include that .h. Now, usage.c doesn't need to know what a struct node is, doesn't need to know what my null is, doesn't need to know the function prototypes, doesn't do any harm to put those things in the include though. Right? The only thing that usage needs is standard io.h, which I include in my stuff.h. But the extra stuff doesn't do any harm. Okay, so now I can compile. Oh, I did something wrong. Yeah, I just lost like 20 points on PA1.
Nice.
Nice.
Good job.
That was easy.
Yeah. Oh, I didn't include all the things, all the function prototypes that I needed. These two right here. Alright, so I'll go down here and I just wrote those out to a temporary file. Alright, so now those are included in my stuff.h. So compile it up, everything compiles fine. Alright, so it was a temporary file. Alright, so I have 4 C programs, I have a .h file, and I have my executable program main. And I can build my executable by just saying gcc-o main star.c, but that's not really optimal. For one thing, if I have other .c files in here that I don't want to include, right, this is going to go ahead and include them, so I should really list the .c files. But also, if I change my usage message, if I decide to modify what that one function prints out, that's a short function. To rebuild my main program, I'm compiling ll.c, main.c, process.c, and usage.c. When in fact, all I wanted to change was this one usage.c, very short function. So this is where a Makefile comes in. Makefile lets you be very succinct and deliberate in what gets compiled when. So let's make a Makefile. So I'm going to call it Makefile. The main thing I'm trying to build is main. And main depends on 4 things. 4 object modules. It does not depend on main.c. If I have main.o, I don't need main.c to build my executable. I can delete my main.c, and as long as I have main.o and process.o and so on, I can still build the executable program main. The problem is if I want to change what main does, I need main.c so I can modify it and recompile. But to build main, I only need those 4 objects. I don't need the .h file. The .h file is only used when I'm compiling these .c's. So those are the only things main depends on. And if I want to compile, this is the line that I use. GCC, set the output to main, and compile those 4 objects. Main.o depends on main.c, and it also depends on ll.h. And to build main.o, I just say gcc-c main.c. I don't name ll.h in here. Right? When I say compile main.c, GCC will open main.c, start reading it, it'll say, oh, here's a line that says include ll.h, it'll open the file, pull the lines out of there, start compiling. So we don't name ll.h here, just like we don't name standard.io.h, even though it's included. So there's a Makefile for main. And each of the .o's, there's the things that it depends on, and there's how we build the .o if the dependencies are met. What happened to my .h file? Oh, my stuff. Alright, so I say make, it compiles all of my .c programs, it links them all together. If I say make again, it tells me everything's up to date. Now if I modify usage.c and I recompile, what does it have to do to get an executable program?
It recompiles usage.c into usage.o, and then it can recompile all the other object files.
Yes.
Because everything else is up to date.
Right, exactly. All it should have to do is recompile usage.c and then link those .o files together to make main. So if I say make, there you go, gcc-c usage.c, gcc-o. Okay, let's touch ll.c. Now main calls things from ll.c, process calls things from ll.c, but that doesn't matter. Main.c is already compiled. It's compiled the fact that it's going to call the init function. Maybe the init function has changed, but that doesn't change what main.o looks like. The only thing that has to be done here is I have to recompile ll.c and I have to relink the objects. So if I say make, it only does those two things. And how does it know? Because that's what we told it in the Makefile. We said main depends on those pieces, and ll.o depends on ll.c. Well, we didn't say that main.o depends on ll.c. So changing ll.c, we didn't have to rebuild main.o. However, if I touch mystuff.h, every one of my .o's is listed as being dependent on my stuff, as it should. If I change what the prototype of a function is, I should recompile all of my programs that might use that function. So now if I say make, it recompiles everything, links it together. All right, so PA1, you did not have to do this. PA2, you really don't have to do this, but you're going to finish PA2 well before the deadline. You're going to have time left over. Start moving towards this kind of approach. Putting things in separate functions, you're required to do that. Putting those functions in separate files. Putting the pieces that you need in common into an include file. And then making a nice Makefile to efficiently build your executable. Right, so try to do that for PA2. I'm not taking off points if you don't, but it's a good platform to experiment with. But do it, you know, in a separate directory once you've got your code in a place where you like it, right? If you start doing this, do it somewhere separate on a copy. Don't do it on your only version of PA2, but experiment with that. All right. I did a little bit of GDB trickery in the first class, but we'll go through that tomorrow. And then I want to start looking at other versions of linked lists, getting rid of the Sentinel, doubly linked lists, circular linked lists. And then we're going to move on to hash tables, probably later tomorrow and for the rest of the week. All right, so I'll see you tomorrow.